Welcome to another episode of Learning. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. This is my channel. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems that have appeared in the CSIR National Eligibility Test July 2025. In this video, we discuss the solution of a problem from the section Algebra, in particular from group theory, and the problem is related to the first and second isomorphism theorems in group theory. And this question is placed in part C, which is a multiple select question. There may be more than one answer and the question carries 4.75 marks. The question ID is 5629546160. Further, this question is suitable for all these examinations. Right, the given question is, let G1 and G2 be subgroups of a given group G. Which of the following statements are true? We are given four options. Option 1, if G1 is normal in G, then G2G1 by G1, the quotient group, is isomorphic to the quotient group G2 by G2 intersection G1. Option 2, if H1 and H2 are normal subgroups of G1 and G2 respectively, then G1 cross G2 by H1 cross H2 is isomorphic to G1 by H1 cross G2 by H2, the direct product of these two groups, and G1, G2 also the direct products. Right. Now, option 3, if G1 is normal in G2 and G2 is normal in G, then G1 is normal in G. Option 4, every subgroup of prime index in G is normal. Right. Let's now discuss the solution of the problem in detail. We have a group G. Given G1 and G2 are subgroups of G. Right. Now, let's call on option 1. If G1 is normal in G, then the G2G1 by G1 is isomorphic to G2 by G2 intersection G1. Right. We recall second isomorphism theorem in group theory. Let H be a subgroup of a group G and N be a normal subgroup of G, then Hn by N, the group, is isomorphic to H by H intersection N. Right. In our case, G2 is a subgroup of G. Given G1 is normal in G, then by second isomorphism theorem, G2G1 by G1, in the place of N, we have G1, is isomorphic to G2 by G2 intersection G1. Right. This is the direct second isomorphism theorem is given in option 1. Therefore, option 1 is true. We move on to the next slide for the discussion of the option 2. If H1 and H2 are normal subgroups of G1 and G2 respectively, then G1 cross G2, the direct product, by H1 cross H2 is isomorphic to the G1 by H1 cross G2 by H2, the product, direct product. Right. This is an exercise problem. I hope that you have done in your class. If not, I will give you a proof of it. We have the group G1 cross G2. Right. and we have H1 is normal in G1, H2 is normal in G2. We are given. So we have the quotient groups G1 by H1 and G2 by H2. Further, we have their direct product G1 by H1 cross G2 by H2. We define a map phi from G1 cross G2, the direct product, to G1 by H1 cross G2 by H2 by phi of the ordered pair, the typical ordered pair from G1 cross G2 group. It is phi of the ordered pair G1 comma G2, small g's G2 is equal to the ordered pair G1 H1, that is the left coset of H1, comma G2 H2, the left coset of H2. Right. For all G1 belongs to G1 and G2 belongs to G2. We claim phi is a homomorphism. We take two typical elements G1, G2, G1 prime cross G2 prime coming from G1 cross G2. Then phi of the ordered pairs, so the product of the ordered pairs is equal to, by definition, phi of G1, G1 prime comma G2, G2 prime. Then by definition of phi, it will go to the ordered pair G1, G1 prime H1, the left coset, comma G2, G2 prime H2, the left coset. Now, H1 and H2 are normal subgroups. Therefore, G1, G1 prime H1 is equal to G1H multiplied by H1 multiplied by G1 prime H1. Similarly, G2 H2 multiplied by G2 prime H2. Now separate them, product in G by H1 cross G by G2 by H2. So it will be ordered pair G1 H1, the left coset, comma G2 H2, the left coset, multiplied by G1 prime H1, comma G2 prime H2. And the first one is phi of G1 G2, the second one is phi of G1 prime G2 prime. Thus phi is a homomorphism. We now calculate Ker phi. The idea is that we will be using the first isomorphism theorem. For that, we calculate Ker phi is a set of all those ordered pairs G1 G2 coming from G1 cross G2 such that phi of the image of G1 G2 is the identity element of G1 by H1 cross G2 by H2. The identity element of G1 by H1 is H1, G2 by H2 is H2. The ordered pair, this is the identity element of G1 by H1 cross G2 by H2. That is the ordered pair H1 comma H2. Now apply phi of G1 G2 is G1 H1 comma G2 H2 is equal to H1 comma H2. This implies G1 H1 is equal to H1 and G2 H2 is equal to H2. G1 H1 is equal to H1 means G1 belongs to H1 and G2 belongs to H2. Right. It is precisely H1 cross H2 because we have to gather all the ordered pairs G1 cross G2 where G1 belongs to H1 and G2 belongs to H2. Therefore, H1 cross H2. The Ker phi is H1 cross H2. Right. We have shown phi is a homomorphism and Ker phi is H1 cross H2. And now we want to show that phi is onto. So you take a typical element of G1 by H1 cross G2 by H2. That is the ordered pair, the left coset G1 H1 comma G2 H2 belongs to G1 by H1 cross G2 by H2. So catch hold of this G1 and G2. So there exists the ordered pair G1 comma G2 belongs to the G1 cross G2 such that phi of G1 G2 is equal to the ordered pair G1 H1 comma G2 H2. So thus every element of G1 by H1 cross G2 by H2 has a pre-image in G1 cross G2. Therefore, phi is onto. Right. Now we recall the first isomorphism theorem. we have two groups, G and G prime, and phi is a homomorphism of G to G prime, and then G by ker phi is isomorphic to the image of G under phi. When phi, the homomorphism is onto, then G by ker phi is isomorphic to G prime. So in our case, phi is onto, therefore applying by the first isomorphism theorem, G1 cross G2 by ker phi is isomorphic to G1 by H1 cross G2 by H2 because phi is onto. So thus we got the option 2. So this says option 2 is true. Right. So far we have shown option 1 and option 2 are true. We move on to the next slide for the discussion of option 3. So G1, G2 are subgroups of the group G, and if G1 is normal in G2 and G2 is normal in G, then G1 is normal in G. Now our question is normality a transitive relation? Let us see, and we give a counter example. Let G be D4, the dihedral group of order 8, and it is generated by rotation R, comma, reflection S, where R power 4 is S square is equal to E identity and RS is equal to SR inverse. R inverse C, R to the power of 4 is identity, R inverse is R cube. These are the defining relations for the dihedral group D4. Now, writing their elements, E, R, R square, R to R cube. So that is the rotations will generate a cyclic group of order 4. S is the reflection, S, SR, SR square, SR cube are the elements. So these are the 8 elements that are there. Let G2 be the group E, R square, S, SR square. This is a group generated by R square, S, and it is isomorphic to the Klein's 4 group. Let G1 is the group generated by S that will give you E, S, and its order is 2. G2 order is 4. So now G1 is normal subgroup G2. Why? The index of G1 in G2 is order of G2 by order of G1, that is 4 by 2, that is 2. And every subgroup of index 2 is normal. So G1 is normal in G2. Also G2 is normal in G, that is the index of G2 in G is order of G by order of G2, that is 8 by 4, that is equal to 2. And every subgroup of index 2 is normal, therefore G2 is normal in G. Note that G1, you take G1, write down the right coset, G1R will be ER, SR, and write the left coset, RG1 is RE, RS. Now it is the set of all, RE is R, RS is SR inverse. SR inverse is SR cube. So the right coset G1R will have elements R, SR. The left coset RG1 has elements R, SR cube. They are not equal. Yes. So therefore G1 is not a normal subgroup G, since every right coset of G1 is not a left coset of G1. Agreed. So thus this tells you the normality is not a transitive relation. Thus option 3 is not true. We move to the option 4. Right. Every subgroup of prime index in G is normal. Not necessarily. We have a counter example. Now consider, let G be equal to S3, the symmetric group on 3 letters, and H is the cyclic group generated by the transposition 1, 2. And it is equal to the identity, the transposition 1, 2. Right. Now, the index of H in G is order of G by order of H. Order of G is order of S3, that is 6. By order of H is 2, that is 3, which is a prime number. Now, but H is not normal subgroup of G. How do you say? Since 1, 3 inverse, take an element of S3, that is 1, 3, the transposition 1, 3 inverse, 1, 2, element of H into 1, 3. G inverse small h G. Right. So that is 1, 3 inverse, transposition inverse is 1, 3 only. 1, 2 multiplied by 1, 3. Yes, you are familiar. No, multiply this. 1 from right to left. 1 goes to 3. 3 fixed. 3 goes to 1. 1 is fixed. 2 fixed. 2 goes to 1. 1 goes to 3. Therefore, 2 goes to 3. 3 goes to 1. 1 goes to 2. 1 goes to 2. It comes back to 2. So that is 2, 3. This is the one does not belong to H. So G inverse HG is not in H. Therefore, it is not normal. So the index of H in G is a prime number, but H is not a normal subgroup of G. Hence, option 4 is not true. So we have seen only options 1 and 2 are true. Therefore, the answer to this question is options 1 and 2. That is the detailed discussion of the solution of this problem from group theory, which is based on isomorphism theorems, first and second isomorphism theorems of group theory. And it is a good question. Right? It also tells you the application of the first isomorphism theorem also. Right. I am sure that you have understood the solution of this problem. Thank you for watching this video. Now, please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Yes, this is my channel. Please subscribe my channel if you have not already subscribed. Yes, I am sure I am going to meet you, all of you, once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.